Hello students, how are you guys doing? It's been a few months since our last video. I have been busy with some other projects. That's why I had to take a break. Anyway, it's happy to be back. I'm happy to be back and this time I'm thinking about starting the course Condensed Matter Physics. Before that, let me discuss some points which might be helpful for cracking CSIR NET JRF exam from my experience. So in order to crack this exam or any other exam, you have to optimize four things. So the first one is very evident, quality. First one is quantity actually. By quantity, I mean the number of hours that you put. So if there is a candidate A and there is a candidate B, if candidate A studies 5 hours per day and candidate B studies 3 hours per day, then definitely candidate A has more chances of winning because he is investing more number of time, more number of hours. Now, the second thing that you have to optimize is quality. Now, when you study, you have to be hungry, you have to be focused, you have to give full attention to the study. You shouldn't be waiting for just one notification in your phone to get distracted. There is no point in studying without any quality for a lot of hours. So even if you are studying 2 to 3 hours or 3 to 4 hours in a day, there should be high quality in your study. The third important thing is that impact. Whatever you are studying, it should come in exam. So this is why you have to go through PYQs, because every time you go through a PYQ, a previous year question, it gives you an idea which topics are important and which topics are not important. So whatever you are studying, it should be coming in exam. It should have a high chance to come in exam. So if there is a candidate who dedicate 5 or 10 days for group theory, then that is not a wise decision. If you are studying for CSIR NET Physics, group theory is not a very common place where the question comes. So you can't dedicate 10 days for that topic. So this you have to keep in mind. Whatever you are studying, it should come in exam, and PYQs will help you in deciding which topics are important and which topics are not. The fourth important parameter or factor that you have to consider is retention. So whatever you are studying, it should stay in your brain. It shouldn't leak. All right. Now, the important thing that you have to do is revision. By revision, you transfer whatever is in your short term memory to long term memory. And also study by using those processes which involve your brain a lot. Like when you are watching a lecture, your brain is not involved too much. Of course, watching lectures help you to clear the concepts, to clear the doubts. But when you are watching a lecture, you can at the same time, simultaneously, you can have a coffee or you can lie on your bed, right? So, in some processes, brain is not involved much. But when you are writing formulas, when you are trying to solve a problem yourself, brain is more involved. So when your brain is more involved, the retention rate, the amount of things that stays within your brain, it is more. So you have to consider all these four and optimize. Then you can easily qualify the exam along with the priors to the creator. So let's come back to the topic, condensed matter physics. Let's start condensed matter physics. In condensed matter physics, we study about solids and liquids. We study about matter which are closely packed, which are condensed. The atoms and molecules are very closely packed to each other. Now, what is the difference between solid state physics and condensed matter physics? In solid state physics, we only study about solids, but in condensed matter physics, we study about solids as well as liquids. Now, solids can be classified into crystalline solids crystalline solids and amorphous solids. Amorphous solids. In the case of crystalline solids, there is a long range of order for the arrangement of atoms, long range order, or you can say there is a definite order, there is a regular order. In the case of amorphous solids, the arrangement of atoms is irregular or random in manner. The arrangement of atoms is in random manner. Now, in the case of crystalline solids, they have sharp melting points. They have sharp melting points. In the case of amorphous solids, not sharp melting points. In the case of crystalline solids, the properties are anisotropic. Properties are anisotropic. Now, by anisotropic, we mean that the properties are different in different directions. So in x-axis, the property has a different value than compared to the value in the y-axis or z-axis. Now, in the case of amorphous solids, because they are randomly arranged, because they are irregularly arranged, whatever is the randomness in x-axis, the same kind of randomness is there in y-axis, and the same kind of mess is there in z-axis. So there is no preferred direction or preferred orientation. So whatever is the mess in x, y, z axis, they gets averaged out and properties are same in all the directions. So we have isotropic properties in the case of amorphous solids. Now let us move on to the next topic, which is classification of crystalline solids. Let's change the color of the pen. So we can classify crystalline solids into single crystalline and polycrystalline. Single crystal, single crystalline, and polycrystalline. In the case of single crystal, we have long range order, perfect long range order. An example is diamond. In the case of polycrystalline solids, there is long range order, but within the grains. So there are lots of grains in these polycrystalline solids. Within the grains, there is long range order. Within the grains, there is order. But in the grain boundaries, the order is interrupted. The long range order is interrupted at the boundaries of the grains. An example, most of the metals and alloys that we see, most of them are examples of polycrystalline solids. Let us continue with the definitions. Now we are going to discuss what lattice is. So these definitions, they are part of crystallography. Crystallography is where we study the arrangement of atoms, how the atoms are arranged in a crystal lattice, that we study in crystallography. And this is very important topic in condensed matter physics, because you have graphite. I'm saying an example. You have graphite and diamond. Both of these contain the same atom. Both of these contain the same carbon atom, but the properties of graphite is very different from the properties of diamond. So what is the reason for this difference in properties? It is because the atoms are arranged differently in graphite and in diamond. So that's why we have to study the crystal structure, how the atoms are arranged in a crystal lattice. So let us first define what a lattice is. It is a set of, lattice is a set of periodic imaginary points, periodic imaginary points. So this word imaginary, it is important. Lattice is not real, it is a mathematical concept. So we put dots. Each of these points, they represent where the atom or molecule is located. So they are not themselves atoms or molecules, they are points in space that we are imagining. Here there could be an atom, here there could be a molecule. So this is an imaginary concept. The whole thing, it is called, the whole thing, it is called a lattice, and each of these points, they are called lattice points. Each of the points are called lattice points. The whole thing, this entire thing, it is called lattice. Now, what we put in each of these points, what we put in each of the lattice points, that is called basis. So basis is physical. Basis is actually existing, but lattice is not actually existing. Lattice is mathematical, but basis is real. Basis is physical. What is the definition of basis? It is an atom. It is an atom or group of atoms or you can say molecule or group of atoms which we place in each lattice points. In each lattice points. Now I have to remind you that each of these definitions, like what is lattice, what is basis, none of this will be asked in CSIR NET exam or any exam. But we discuss this for the completeness of the syllabus and for the completeness of the understanding. So once we have lattice and we put basis in them. So let's say I put a molecule or an atom here, a molecule here. Let's say this is representing molecule, a molecule consisting of a larger atom and a smaller atom. So when I put this molecule in each of the lattice points, now this is a crystal structure. Now this is not lattice. Now this is crystal structure because I have placed basis in the lattice point. So when you add lattice and basis, what you get is crystal structure. Lattice plus basis is equal to crystal structure. Let's move on to discussing unit cell. A unit cell is like a brick in the wall. You have to repeat it. You have to translate it in 3 dimensions to get the entire crystal structure. So unit cell is the smallest repeating structural unit of a crystal lattice that when translated in 3 dimensions, we get the entire crystal structure. And also you should note that there shouldn't be any gaps. There shouldn't be any voids. Now there are two types of unit cells. One is primitive unit cell. In the case of primitive unit cell, we have effective number of lattice points equal to 1. In the case of non-primitive unit cell, we have the effective number of lattice points equal to, not equal to, it is more than 1. So in the case of primitive unit cell, we have effective number of lattice point equal to 1. In the case of non-primitive, it is more than 1. Now, what do we mean by effective number of lattice points? Let's discuss that. So here we have a simple cubic unit cell, simple cubic unit cell. Now, if I ask you, one might say that the number of lattice points here is 8, because here you have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 lattice points here. But if I ask you what is the effective number of lattice points, the answer is not 8. It is actually 1 by 8 times 8, which is equal to 1. So this is a primitive unit cell. Simple cubic unit cell is a primitive unit cell because the effective number of lattice points in it is 1. Why we are multiplying with 1 by 8? Because this lattice point at the corner, all of it is not inside the unit cell. Only 1 by 8th part of it is within the unit cell. Only 1 by 8th part is within the unit cell. You can see this figure. Let's cut atom. It is 1 by 8 lattice point. So if you consider any lattice point in the corner, only 1 by 8th part of it is within the unit cell. That's why we are multiplying with a factor of 1 by 8. And there are 8 corners, so you have to multiply by 8. This is equal to 1. So when we have effective number of lattice point equal to 1, then we say that the unit cell is primitive. Here is an example for a non-primitive unit cell. So this unit cell is body-centered cubic unit cell. We write in short as BCC. So what is the difference from simple cubic? In simple cubic, we had lattice points at the corners only. But here, along with the corner lattice points, we have a lattice point at the body also. And that lattice point, it is entirely within the unit cell. So if we write the number of effective lattice points, we have 8 corner lattice points. Each of them, 1 by 8 of it is within the unit cell. So 8 into 1 by 8 for corner lattice points, plus one lattice point is entirely within the unit cell. Therefore, total number of effective lattice points, this is equal to 2. Therefore, BCC is non-primitive. Similarly, another example for non-primitive unit cell is FCC, face-centered cubic unit cell. In this case, along with the lattice points at the corners, we have lattice points at the faces also. So we have 6 faces for the cube. So this is a face. In this face, at the center of the face, we have a lattice point here. Similarly, for this face, we have a lattice point here. And similarly, we have 6 of them. Now the question is, how much part of the lattice point at the center of face is within the unit cell? So you can see half of the lattice point is within the cube and half is outside. So 1 by 2 times how many faces are there for a cube? 6 faces are there. Plus at the corners we have 1 by 8 of lattice points, and how many corners are there? 8 corners are there. So total number of lattice points, or we can say effective number of lattice points in a face-centered cubic unit cell is 1 by 2 times 6 is 3, and plus 1 by 8 times 8 is 1. So total 4 is the answer. Let us distinguish between the lattice vectors, primitive lattice vectors, and translation vectors. So first of all, lattice vectors. Lattice vectors are vectors that connect any two lattice points. So let's consider this lattice point and this lattice point. If we draw a vector, connecting these two, so this vector is called a lattice vector. Now, primitive lattice vectors, they are special vectors which are vectors of smallest magnitude which can form a unit cell. which can define a unit cell. So let's say this is vector A. Let's say this is vector B, and let's say this is vector C. So A and B form this parallelogram. A and B form this parallelogram. And when we consider C also, which is not in the plane of A and B, then we get this. Then we get this unit cell. This unit cell we obtain this parallel epiped formed by A, B, and C. So we call A, B, and C here. They are primitive lattice vectors. Why primitive lattice vectors? Why they are called so? Because they are defining a unit cell. They are lattice vectors of smallest magnitude, which is defining a unit cell. Now, what is a translation vector? Translation vector T, it is written as n1a plus n2b plus n3c. So translation vector is a linear combination of primitive lattice vectors. Here n1, n2, n3, these are constants. n1, n2, n3 are constants. A, B, and C, these are primitive lattice vectors. So to translate to any point in a crystal lattice, we do a linear combination. We do a linear combination of primitive lattice vectors. And if n1, n2, n3 are integers, then in that case, the lattice is called bravais lattice. So bravais lattice, in the case of bravais lattice, we have translation vector T is equal to n1a plus n2b plus n3c. And here n1, n2, n3 are integers. n1, n2, n3, they are integers. They belong to Z. Now there is also another definition for bravais lattice, which is each lattice point in a bravais lattice, each lattice point has identical surroundings. Identical surroundings. Now one of the point to note here is that this A, B, and C, they may not be always perpendicular, but the condition is that all of the three cannot be in the same plane. One of them should be in a different plane. So for bravais lattice, there are two definitions. One is translation vector is given by n1a plus n2b plus n3c, where n1, n2, n3 are integers. The second definition is in the lattice, each lattice point has identical surroundings. Now let us consider a honeycomb lattice. In this case, let us consider an atom here. So there is an atom here. Let's say this is atom 1, and let us consider another atom which is here. This is atom 2. Now, is the environment of atom 1 same as environment of atom 2? The question is the environment of atom 1 same as the environment of atom 2? Because we have to decide if this honeycomb lattice is a bravais lattice or not. So how do we check that? The definition is each lattice point has identical surroundings. So from the definition, for this to be bravais lattice, 1 and 2 should have identical surroundings. But what we see is they have different surroundings. For atom 1, if you move to upside, just on the top of it, you have an atom at this distance. At this much distance, you have an atom. Here you have another atom. But for the atom 2, you have to move a larger distance to reach to another atom. To reach to this atom, you have to move a larger distance. Now, in the case of atom 2, towards the left and towards the right, you have atoms just after moving this much distance. But for atom 1, you have to move this much. You have to move up to this distance to get an atom to right and left. So their environments are different, and that's why honeycomb lattice is not a bravais lattice. Now, bravais lattices also satisfies some of the symmetry properties like translational symmetry, rotational symmetry, inversion symmetry, etc. But let's not discuss that. So in 2D, we have 5 types of bravais lattices. So that is given here. When A is not equal to B, when the magnitude of A not equal to B, and theta is not equal to 90 degree, then we have oblique. The second is rectangular, and there is primitive rectangular and non-primitive rectangular is there. Third, we have square. In the case of square, we have A is equal to B, theta equal to 90 degree. In the hexagonal, we have theta equal to 120 degree. A is equal to B. So there are 4 types of crystal systems in 2D and 5 types of bravais lattices. In 3D, we have 7 types of crystal systems and 14 types of bravais lattices. 14 types, 14 bravais lattices. Now, I'm not going to discuss each of them in detail. Here, A, B, C are the lattice side lengths. Okay. And alpha, beta, and gamma are angles. Now, in the next video, we will start with the reciprocal lattice. See you there. Thank you for watching.